We had worksheet number 16 for homework last night. We have the answers up on the board here, and some people have asked me to go over question 2, 4, and 5 on worksheet number 16. So we'll do that right now. Starting with number 2. It says a 7-centimeter tall object is placed 4 centimeters in front of a diverging mirror. The first thing that we probably should do when we read this question is circle that word diverging. Why? What is there in that word, diverging mirror, that can lead us to a silly mistake or a very simple but important mistake? What do we got to remember with every diverging mirror? Good. The focal length is a negative value. So I would write that right away. As soon as I see that word diverging, I would put F is a negative, just to remind myself that when I go to write down my givens, when I go to plug it in, then I'm going to put it as a negative number. Calculate the image distance, the image height, and the magnification of the image, as well as the characteristics. We have an object height here of 7.00 centimeters, and we have an object distance of 4.00 centimeters. We have a focal length here of negative 8.00 centimeters. I'm not forgetting to put the negative in there because I reminded myself when I first read that it was a diverging mirror. We want to find the image distance, di. We want to find the image height, hi. And we want to find the magnification, as well as the characteristics, which we'll worry about after we've calculated these values. To find di, it probably makes sense to use the mirror equation. 1 over f is equal to 1 over do plus 1 over di. 1 over negative 8 equals 1 over 4 plus 1 over di. Now, the simplest way to do this is with that little trick that I taught you on our calculators. Let's say negative 8, x to the minus 1, subtract 4, x to the minus 1, gives me negative 0.375. But I want to flip that over because that's not di, that's 1 over di. So let's flip that over. We get a di of negative 2.666. We're going to write down the unrounded number there because we may need that number later on in another calculation. So di is done. We can find hi now. Let's find magnification now. M is equal to negative di over do. It's also equal to hi over ho, but I don't know the value of hi right now. So let's use di over do. Negative 2.6667 centimeters. Why did I go negative? Di is a negative value, but we want to take the negative of the negative value. It's always negative di, whatever di happens to be. We divide that by do, which is 4.00 centimeters. We do the math on that one, and we end up getting 0.667. And there's no units associated with m. Sometimes you might see it written as 0.667x, like you do in biology class, right? When you're drawing your diagrams for your microscope, you write down 40x or 400x. Or you can just leave it as 0.667 if you want. Now we want to find the image height. All we can do at this point is say m is equal to hi over ho. And we rearrange that to solve for hi. It becomes m times ho. 0.667 times the object height of 7.00 centimeters. We do the math on that one, and we get 4.67 centimeters. Now, what about the characteristics? Well, we can tell by this whether it's real or virtual. A negative di tells me that it's a virtual image. We get a positive hi, which tells me that it's an upright image. And we get a magnification that's 0.667. It's between 0 and 1. That tells me the image is going to be smaller than the object. We're going to have a number that's bigger than 1 if we have an image that's bigger than the object. Is that okay? All right, the next one we needed to go over is question number 4. It says a store owner uses a diverging mirror with a radius. Diverging, once again, let's write down F is a negative value. With a radius of curvature of 1.00 meters to keep an eye on shoplifters. How tall would the image of a 1.80 meter tall man be if he were standing 5 meters in front of the mirror? The radius of curvature is 1.00 meters. We don't use that anywhere other than finding the focal length. What's the focal length if my radius of curvature is 1? What is it? Good, 0.5. And it's going to be negative 0.5 because once again we're told that it's a diverging mirror. We're in meters this time. Usually we're in centimeters, so be careful about that as well. We have an object, a man, that's 1.80 meters tall, and presumably he's standing on his feet, not his head. Therefore, HO will be positive. He's standing 5 meters in front of the mirror, so DO will be 5.00 meters, and it's always going to be positive for us. We want to find HI, the height of the image here. There's only 2 equations to try, so try one of them. Yeah, I'm going to say 1 over F is equal to 1 over DO plus 1 over DI. We're not looking for anything in that equation, but I think that we're going to need something to find HI. I think we're going to need the value of DI here. Let's find it. If in the end I was wrong, we didn't need that value, it's not a big deal. It just means that we found something that we didn't need. It's not wrong. We got 1 over negative 0.500 equals 1 over 5 plus 1 over DI. Let's go to the calculator again and do that little trick. Negative 0.5 subtract, be negative 0.5 x to the minus 1, subtract 5x to the minus 1. Let's flip that over, and we get negative 0.4545. Right, Rob? Now, that's not the value that we're looking for, but we've got it if we need it here, right? So let's try to find HI now. At this point, I'm probably going to use the magnification equation. HI over HO equals negative DI over DO. If you want to just say M is equal to negative DI over DO and then set M equal to HI over HO, that's okay. But because these 2 terms are equal to each other, I can set them equal to each other right off the top here if I want. HI over 1.80 meters equals negative 0.4545 over DO, which is 5.00. When I do that, I think I get 0.162. Dan said he got positive 0.163. There might have been a rounding issue there for one of us. I'm not sure whether it's me or you, but obviously you did it right. 0.164. Okay. I'm sorry? Oh, okay. So we'll say 0.164 then, yeah. So somewhere I made a rounding issue in there somewhere. That's going to be meters, right? Good. And the other one, the final one that we needed to take a look at with this was question number 5. This one's a bit of a mouthful right off the top here. It says the inverted real image of a 6 centimeter tall candle. Let's say when we see the word inverted, let's right away just write down HI is negative. Okay, we may or may not need that information, but we're going to write it down just in case we need it. We have a real image. That tells me that DI is positive if it's a real image. Again, I might not need that, but I'm writing it down just in case. The object, the candle, is 6 centimeters tall, so we're going to make that HO 6.00 centimeters. We'll assume that it's right side up. It's found to be twice as tall as the actual candle, the image that is. That means M is going to be 2.00, but we're going to stick a negative in front of it. How did I know that? How did I know that it's going to be negative? It's 2 because it's twice as tall as the actual object is. But how did I know right away that it was negative? Holly? Good. The first word that I read, or the first phrase that I read, the inverted image. If it's an inverted image and it's a right side up object, then m is going to be a negative value. The candle is 15 centimeters from the mirror, so DO is 15.0, and it's positive because it always is. The focal length here is going to be 10.0 centimeters. How do you know that it's positive? We're not told that this is a real image or a virtual, we're not told that it's a real focal point or a virtual focal point. So how do I know that it is a real focal point, that it's a positive value? This one's a tough one. If you didn't even catch that, and you made it positive just by default, then you got away with it. But we should know why it's positive, just in case there's that time when it's not positive, it's a negative. Why is it positive? If we get a real image, it has to be a concave or a converging mirror. Think about your ray diagrams. Every time you had a diverging mirror, you got a virtual image formed. We're told that it's a real image. Now, you don't always get a real image with a converging mirror, but you never get a real image with a diverging mirror. So this has got to be a converging mirror. Therefore, the focal point has got to be a positive value. We want to find the image height here, HI. We want to find the image distance, DI. And then we want to find the characteristics, which we'll worry about after we've calculated those values. If in doubt, I usually start off with this equation, the mirror equation. 1 over F is equal to 1 over DO plus 1 over DI. 1 over 10 is equal to 1 over 15 plus 1 over DI. Let's solve for DI. I'm looking for DI, so that seems to work out for us here. Say 10, x to the minus 1, subtract 15, x to the minus 1, gives me this value. I'm going to flip that over to get DI. We end up getting 30. Should be 30.0 centimeters. Okay, first one done. Now let's find HI. We know that M is equal to HI over HO, and M, we're told, is negative 2.00. We want to find HI. Go ahead. Okay, good question. Let's go through this and then we'll address that. HI is equal to M times HO. M is equal to negative 2.00. HO is 6.00. That gives me an image height of negative 12.0 centimeters. Okay, let's look at the characteristics here. Okay, we know that it's larger. We're told that it's twice as big. We know that it's inverted because the image height is negative. And we know that it's real because we're told right on the third word of this question that it's real. Now, Patrick just asked a really good question. He said, you know, we're told that it's twice as high as the actual candle. Do we need to go through that equation and show that it's negative 12? No, but be very careful if you just, if you don't go through that process, okay? You know that it's 12, right? You know that it's twice as big and the object was 6 centimeters tall, so you know it's going to be 12. But the image height is technically negative 12 because it's inverted. If you just assume, you just read the question and say, oh, it's twice as tall, okay, I'll multiply it by 2, what are you going to get? Positive 12, right? Yeah, absolutely. If you note that it's negative because you caught that right in the beginning here, then that's absolutely fine. I'm fine with you using that process. Okay, but I think that there's a greater chance of missing that negative if you don't do it this way. If you can do it without missing the negative, just by reading the question, then that's fine. Any more issues on this page? Yep. Yep. 6 is the one where we said we had to assume that it was a converging mirror, even though it didn't say that. You should have been told that it's a converging mirror. Okay, there's no other way to do this, okay, if you don't assume that it's a converging mirror, and therefore that F is a positive value. Again, you should have been told that. I just missed that. We have an object height that's 5 centimeters tall here. We have an image that's produced 7 centimeters behind the mirror. That's going to be DI. Now, how do we know that DI is positive or negative? What is it, first of all, positive or negative? It's going to be negative. Why is it going to be negative? If the image is produced behind the mirror, think back to your ray diagrams. Picture them in your head right now. Your ray diagrams show you that if you have an image produced behind the mirror, it's got to be a virtual image. Images produced on the same side of the mirror as the object are real. This is going to be -7, virtual image, because it's on the other side. The radius of curvature is 10 centimeters. That means we're going to make our focal length 5 centimeters. And as I said, we had to assume that it was a concave or converging mirror, which you weren't told, but you should have been, making it a positive focal length. We want to find M. And again, the last part of the question says determine the type of mirror. You can't do that. You can't do that. You had to make that assumption. So let's find M here. M is equal to HI over HO equals negative DI over DO, but I don't think I have enough information. So let's go back to that equation that I almost always start with. 1 over DO plus 1 over DI. 1 over 5 is equal to 1 over DO plus 1 over negative 7.00. Let's go back to the calculator and pull that little trick here. Let's say 5x to the minus 1 plus 7x to the minus 1. Why did I add that over? When I'm taking something over, don't I usually subtract it? Yeah, what we're doing really is subtracting a negative 7 or adding a plus 7. Right? Since it's negative on the right-hand side, we take it over to the other side by adding. We get that number, we flip it over to get DO, we get 2.917. Now we're going to find M. The easiest way to find M at this point is to say negative DI over DO. So it's going to be negative 7 over 2.917. And when we do that, we get positive 2.40. Tells us that it's upright, it's bigger, and we already know that it's a virtual image. Right? So if you made that assumption that I told you you had to make, even though it wasn't given to you in the question, this is what you should have gotten. All right, we also had a couple questions on our Snell's law stuff. That was questions 1 and 2 on page 668. Snell's law, if you remember, says sine theta 1 over sine theta 2 equals v1 over v2 equals lambda 1 over lambda 2 equals n2 over n1. Okay, that's all on your data sheet, so you don't need to worry about that. But you do have to be careful that you check your data sheet and don't mix it up and say n1 over n2. Any issues with 1 or 2 here? 1 and 2? Okay. All right, let's take a look at number 1 then. It says light passes from a diamond. The index of refraction of a diamond is 2.42, and that's on that table that you had in your book and in these notes here. The angle of refraction, the index of refraction for air is 1.00. On that data sheet, it actually says 1.0003. I'm using 1.00 because your Physics 30 diploma exam data sheet says 1.00. So we're just going to be consistent with that. We may get a slightly different answer than what appears here, but I think it's probably going to round to the same thing. And 1 coming from diamond and 2 going to air. The angle of refraction, we're going to call that theta 2, is 25 degrees, and we want to find theta 1. So we know we've got 4 parts to this equation, and we know we're only going to use 2 parts ever. In this case, since we're looking for theta and we have n, let's use sine theta 1 over sine theta 2 equals n2 over n1. Theta 1 is what we're looking for. It's over sine 25 degrees equals n2, which is 1.00 over 2.42. Let's do this one on our calculators. Let's say 1 divided by 2.42. That equals 0.413. Let's multiply that by sine 25. Make sure you're in degree mode on your calculators. Becomes 0.1746. Now, what I've just solved for is not theta. What I've solved for here is sine theta. Now, how do I get theta? Second function tan, or inverse tan. Sine, I mean, sorry. Tan, where did that come from? We get 10.1 degrees, or round it to 2 digits, it still ends up being equal to 10 degrees. Is that good, Rob? Number 2 says light traveling from air into a transparent material is incident at an angle of 20 degrees and refracted at an angle of 17. What's the index of refraction of the transparent material? This is going to be theta I, theta 1 I should say. This is going to be theta 2. N1, it's going from air, N1 is 1.00, and we're looking for N2. Once again, we're going to use the sine theta 1 over sine theta 2 equals N2 over N1. This time we're going to rearrange to solve for N2. Let's plug in some numbers here. Let's say sine 20 degrees over sine 17. N1, we get lucky here. If the index of refraction of air is 1.00, then N2 divided by that is just N2. Do this on our calculator. Let's say sine 20. Let's get a number for that. Press equals. Let's divide that by using some brackets. Sine 17. Okay, 1.16. Then we multiply that by 1, which of course is going to end up being 1.16 or 1.17. Good? Yes, yes. The question was, if you didn't hear it, on the final exam, are you given the indices of refraction? You won't be given the table as it was given to you in your notes and in your textbook. What will probably happen if you need an index of refraction other than air, which is just 1.00, that's on your data sheet, actually. If you need an index of refraction other than that, it'll probably be buried in a half a page or a full page of information, right, where it says, use the following information to answer the next 6 questions. It'll tell you that along with a whole bunch of other stuff. You'll have to find it in that page of information, but it'll be there. You don't have to memorize anything. Even air you don't have to memorize, and it's the simple one. Yep, Bryce? Yeah. All right, we're going to do another example in just a second here, but right now I'm going to assign for you for homework questions 3 and 4 on page 668. So finish off 3 and 4 for homework. We're going to do one more example, and there's going to be a couple of questions that go along with that. Then essentially, I'm going to give you the rest of the time to work on it in class. Here's the next example. 13.4 on page 670. It says a ray of yellow light with a wavelength of 570 nanometers travels from air into diamond. Air into diamond. Okay, N1 is 1.00. N2 is 2.42. Now, you don't have to have those numbers memorized. I just do because we use them fairly often. Okay, I know it's going from air, N1, to diamond, N2. And it's striking at an angle of 30 degrees. So that's going to be theta 1. If it goes in at an angle of 30 degrees, that's theta 1. We have a wavelength of light. We'll call that lambda 1. Okay, that's the wavelength that it is as it's going in. We want to find the speed of light in the diamond. In other words, we want to find V2, and we want to find lambda 2, the wavelength of the light as it goes into the diamond. There is only one equation, really, that we use here, but there's 4 parts to it. Try things until you get what you're looking for. Okay, we have N1 and N2, so odds are we're going to use those values, the N2 over N1 part of the equation. If we want to find V2, then we're probably going to use the V1 over V2 part as well. V1 over V2 equals N2 over N1. V1, what's V1? What's the speed of this yellow light before it goes into the diamond? 3.0 times 10 to the 8. Okay, we got to read between the lines a little bit there, right? But it's there. The speed in the air is 3.0. The speed in the diamond, that's what we're looking for here. N2 is 2.42. And if we use that value of 1.00 instead of 1.0003, then we have a little bit easier math here because we don't have to divide by anything. Yeah, that's lambda 1, yes. All right, let's solve for V2 now. The V2 goes up by multiplying. The 2.42 goes down by dividing. V2 ends up being equal to 3.0 times 10 to the 8 divided by 2.42. We end up getting 1.24 times 10 to the 8 meters per second. So that you can see, in diamond, light slows down dramatically, okay, by a factor of 2.42. Now let's find a lambda 2. We're going to do this in a pretty similar way. Lambda 1 over lambda 2 equals n2 over n1. Lambda 1 is 570 nanometers. Do we have to convert that to meters here? It's never a bad idea, 570 times 10 to the minus 9. But if you leave it in nanometers, it's okay. Because when we solve for lambda 2, we're just going to get the value in nanometers. So 570 over lambda 2 equals 2.42 over 1.00. And we're going to rearrange this in the same way. Lambda goes up, 2.42 goes down. 570 divided by 2.42 gives me 236. What are the units for that now? Usually we're in meters, right? But since we didn't convert there from nanometers to meters, it's 236 nanometers. Okay, let's think logically to see if this makes sense now. We went from a low to a high index of refraction. What's going to happen to the speed as we go from a low to a high index of refraction? It's going to decrease. Has it decreased here? Dramatically, yes. Okay, so we're probably right there. What's going to happen to the wavelength as we go from a low to a high index of refraction? Well, when speed decreases, wavelength also decreases. So it should go down by a factor of 2.42. Has it? Yes. It's less than half of what it was when we started. All right? It is 11:18. You have the next 11 minutes to work on the two questions right here on page 668, 3 and 4, in addition to these three questions that you see on page 670. That's it for today.